Bismillah ar-Rahman ar-Rahim. Let's continue with Boolean Algebra chapter. We already saw in the last video basic theorems that enable you to simplify or to manipulate Boolean expression. Let's continue with this to see more theorems or more laws like commutative law. It is the same law that we have in the ordinary algebra. So commutative law can be applied for the AND operation and for the OR operation. For the AND operation, if we have two Boolean variables A and B, so A and B is also equal to B and A, because this is done by the same logic gate, two input and logic gates. So whatever we put here, A or B at this pin or here, it is giving always the two pins ended, the two values on the two pins ended together. So it will be A and B or B and A similarly. This is also applied on the OR operation. So for the OR operation, if we OR A with B, this is as we OR B with A, done by the same logic gate. Or, so if I in here at this pin the value A or the value B, it is giving always the two values at the two pins or together, so it is giving always A or B. This is the commutative law. Associative law, we can also apply it on the AND operation. So if I have three Boolean variables A, B, and C, and we AND A with B ended with C, means we AND first B and C, then the result ended with A. This is as we AND A with B first, then the result ended with C. And in Boolean algebra, we write even A, B, C without parentheses, and all is giving the same result. This is applied also on the OR operation. So if I OR A and B and C variables, and I start by ORing first B or C, then the result ORed with C, it is equal to, if I OR A with B first, then the result ORed with C, and we don't even need parentheses because we can just write A or B or C. Okay, this is very easy as in the ordinary algebra. You know already all these things. Distributive law. Distributive law, here we have two laws. We distribute the OR operation over on the AND operation, and the opposite, yani we distribute also the AND operation over the OR. So first let's write the first theorem in the distributive law. So if I have A ANDed with B or C, this is equal to A and B or A and C, as we have in the ordinary algebra. But the second one here, this one is not valid on the ordinary algebra. If I write A or B ended with C, this is equal to A or B ended A or C. So I am distributing the OR operation over the AND operation. I have A or B. I will OR A with B, then I will OR A with C. Okay, so how we can prove this? This is very easy. If you want, we can develop this expression, this second side of the expression. If we develop it, we need to obtain this first part, that is A or B ended with C. So let's develop. let's open the parentheses. This is giving. So first we start with A as we do in ordinary algebra. So A and E is equal to A and E, or now we end A with C, or A and C, plus now B with A, plus B and A, now B with C, so plus B and C. This is equal to A and A is equal to A, as we did in the previous video, or A is C, or B and A, B ended with A is equal to A ended with B, because the AND operation is commutative. So I can write also A and B, or BC. So what we can do here, we can put common factor. So the three terms here, they have common factor A. I can put it factor out. So here it will be A and 1 plus C plus B, or BC. This is equal to what? All this expression is equal to 1, because as you know, 1 ORed with anything is giving 1. So I will have A ended with 1. A ended 1 is equal to A, or BC. So we get this, that is the second part of our law, that state that A or BC is equal to A or B ended with A or C. Okay, it's not very complicated, but you need to practice in order to master this law. De Morgan's law. De Morgan's law is something very beautiful in Boolean algebra, because it will enable us to do many things. It will enable us to simplify very big expression under the complement operation. So what states De Morgan law? It states that if I have the NAND operation, so A or B, sorry, the NOR operation, this is a NOR, A NOR B is equal to A complement and B complement. This is very interesting. Why? Because this means that if I have a NOR logic gate, this is the NOR logic gate with the two inputs A and B. So here I have A NOR B. This is equivalent to what? This is equivalent to the variable A inverted, the variable B inverted, and ANDed together. So it seems we are converting a NOR operation to AND operation, but where the input are complemented. So this is equal to A ANDed, A complement ANDed B complement. This is the first De Morgan law. The second De Morgan's law, we apply it on the NAND operation. So if I have A NANDed with B, this is equivalent to A complement or B complement. So what means this? It means if I have a NAND logic gates, I can convert this logic gate to what? To a NOR logic gate, sorry, to an OR logic gate, but where the inputs are inverted. So first I need to invert the input A, I need to invert the input B, then they are NOR together, and I will have here A bar or A complement ORed with B complement. This is De Morgan's law. You need to practice to solve more examples in order to master this law. And let's see in the next video how we can use De Morgan's law to simplify very big expression where you have many operations under the inverter or under the complement operations. Okay?